So we'll pick up where we left off last time, but remember there's no lecture on Monday of the Thanksgiving week, and there's no lab on Tuesday, and we won't be holding any help hours all next week. So we'll come back after the break. But I did want to pick it up from where we left off last time by, again, reviewing all of the complexity that we've looked at so far, or the efficiency that we've looked at so far. Right? We started out with linear search, right? And we said that we're going to quantify work here as far as the number of comparisons. And linear search, because of where it's got its name, is going to make about n, or here I'll say approximately n comparisons to search for something. Of course, it's adaptive, so sometimes you get lucky and you find it in the first spot. Sometimes you get unlucky and you find it in the last spot. Sometimes you can just take the average and look at n divided by 2. Right? And so if there are a million elements in the array, then you can expect about 1 million comparisons or half that or something like that. Right? Then we looked at binary search. Binary search. Right? Where it was approximately log n. Right? And remember that our logs are going to be log base 2 implicit there, which is an exponential speed up. But of course, binary search required that the entire array be sorted to begin with. So we went and developed a sorting algorithm called selection sort. Right? And we analyzed that pretty quickly last time. I think I made a mistake. But at the end of the day, it's going to end up being n squared. Right? I think that the mistake was I was off by 1 or something. Ultimately, it's going to end up being something like the following, right? Where it's n times n minus 1 all over 2. Right? That's what we would have gotten in the end. Okay. Now, if you expand that out, of course, you're going to have 1/2 n squared minus 1/2 n. Right? Now, what about this this one right here? Right? Should we even consider that? That's like taking something off. Not only that, but it's a lower order term, right? Which one of these terms is really going to matter as you go off to infinity, as your array sizes go from 1,000 to 1 million to 1 billion to 1 trillion? This one is going to dominate far more, right? We can go ahead and safely ignore this one over here. What about this constant coefficient sitting out front here? Just like the linear search, when we looked at that, we said, we don't care about that 1/2 for the average case versus the 1 for the worst case, because at the end of the day, there's some other hidden constant sitting out front, C, that is quantifying the number of nanoseconds or milliseconds or whatever to actually execute the half as much. It'll be twice as quick, right? Twice as fast. So ultimately, we don't care about this either, right? So we're going to get rid of both of those two things together, and we're going to say that it's simply about n squared. Okay. Now, how bad is that? Right? Well, again, let's go through that same analysis that we've done before. What if you took the first derivative of this, if you're familiar with calculus, right? That gives you the rate of growth, right? So what is the rate of growth of this thing? 2n. In other words, it's linear. The rate of growth is linear. Contrast that with binary search, where the rate of growth is actually going down, right, as it gets bigger and bigger. Contrast that with linear search, where the rate of growth is constant. Now it's no longer even constant. Now the rate of growth is actually growing. Right? Look at it another way. What if I went from an input size of n here, and it took, say, time t, which is quantified by n squared somehow, right? Again, approximately, right? And then I went up on order of magnitude, either 2n or I went up to, say, 10n. Right? How does that change the dynamic here? Well, I'm going to plug in 2n here for my n, which is going to be ultimately squared. Right? Okay. So now just use algebra here. What's that equal to? 4n squared. In other words, when I go from here to here, it is 4 times slower. Right? When I double the input size. When I go from 1 million up to 2 million, it's going to be 4 times slower. Let's go up in order of magnitude so that we can really understand this. Right? 10n squared. If I go up in order of magnitude, that is equal to 100n squared. In other words, 100 times slower. Right? At least that's from the perspective of this theoretical analysis here. Let's come over here and measure it. Right? So, the selection sort, binary search, whatever. Let's go ahead and I can go ahead and leave this here. We already printed the array, so I'm going to go ahead and get rid of this. Right? And let's go ahead and call one of these functions that I pulled in from Hack6 to generate a random array. Okay? So we'll just come down here and start with a brand new array. Int BUR is equal to generate a random array of size, say, n is, we'll start out with 1,000 here. 1,000 elements, n. Right? And then I'm going to selection sort it. Right? Selection sort BER on an array of size n. Right? I don't want to print it out here because I don't want to look at 1,000 things. Right? But let's go ahead and get rid of the rest of this code for now. Right? Just to make sure that it's not going to impact our efficiency here. GCC demo. Right? All right, so if, int n, there we go. GCC this, there we go. Now if I were to run this, of course it's going to be very, very quick, but that's because there are only 1,000 things in there. Even a slow computer by modern standards, like a 20-year-old computer, could still do this pretty quickly, indistinguishable to the human eye, right? So let's actually start to measure it. Hopefully you've gone through the PDC modules in which we introduce you to this time utility, right? It will actually tell you that the real time, that's the wall clock time. That's the time that has passed in the physical world, right? The user time, that's how much time your actual program was running on the processor. And then the system time, that's how much your program had to pause so that the system could do system stuff. Ours was so quick that it didn't need to do that. But what if I jump up an order of magnitude, go from 1,000 to 10,000? It was measurable here, right? What's your prediction based on what we did over here? Right? If it goes up by an order of magnitude, it'll be 1,000 times slower, or roughly 1,000 times slower, right? So, or not 1,000 times, 100 times slower. So you'd expect about 0.2 seconds, right? Oops. And let's do that again. There we go. Not exactly, but that's because, you know, it's still small here, right? But it is going up by a factor here, 35 times, right? That's slow, right? Even though we only went up by a factor of 10 here. Let's go up by another factor of 10, 100,000, and recompile it and run it, right? This will be 100 times, roughly 100 times slower, which would end up being about 7 seconds. We're not going to have that much, though, right? But it starts to become noticeable, very, very noticeable. Oh, maybe it will be 7 seconds total. Right? Yeah, it will be. Right? We went up by an order of magnitude, and it's 100 times slower. 100,000 things, 100,000 integers in particular, is that big data? That's only 400K, right? That's not even a megabyte of data, right? Why the heck is it so slow? Let's go up another order of magnitude here. Should I even bother letting it run? 7 seconds. 100 times slower is going to end up being 700 seconds. 700 seconds is 11 minutes, 12 minutes, something like that. Right? So we'll go ahead and let it run in the background there, see if we actually get an answer. Right? What I want to know is, can we do better? Okay. And to do that, I'm going to introduce you to another algorithm here that's much quicker. That's where it gets its name, by the way. Right? So here's the basic idea. I'm going to visualize the basic idea, and then we can write some notes on it if you want to. But what I'm going to do is I'm going to use a divide and conquer strategy. I'm going to take the idea from binary search, where you can cut the problem in half, and you can ignore half the problem, and then only process this other half here, which led to an exponential speed up. What I'm going to do is I can't ignore half of this array, right? If I just sorted this half and then left this and ignored it, that wouldn't work. But I can do something similar. What I can do is I can choose what's called a pivot element. Right? And what I'll do is I'll go through the rest of the array, and anything that's smaller than the pivot element, I'll put the left side. Anything that is greater than the pivot element, I'll put on the right side. So let's go through this. 4, 9, 4. All those things are less than 42. So 4, 9, 4. When I get to 102, though, that's greater than this pivot element over here. What I'm going to do is I'm going to shove it over to the right, 102. There we go. 34 is less, so I'll put it over here. 12 and 2 and 0 are all lefts. All right. Once I've gone through this process, this is called partitioning, where should I put 42? Yep, right there in between them, right? So I'll go ahead and shift 42 down here, and I'll even put it into a box. There we go. All right. Now, why did I put it into a box? Everything over here is less than 42. Everything over here is greater than or equal to, if you've got ties, 42. Do I ever need to move 42? It's right where it needs to be. We end up putting the pivot element right where it needs to be. and have now two smaller arrays, right? We've got a left partition and a right partition. And here's where the divide and conquer comes up. I've divided it, right, into a left partition and a right partition. Now conquer it by sorting this subarray and sorting this subarray over here. We'll come back to this one. What about this one right here? Right? When I go to that subarray, is there anything to sort? No, there's one element. By definition, it's sorted. Right? So I'm done over here. There we go. And imagine that these are all glued together. All right, let's do that process one more time. Right. Oh, come on, copy. There we go. Nope, no, that's not what I wanted. Close that. I said copy. I think it's the... All right, fine, I'll cut you. And paste it. There we go. And get rid of that P. There we go. I'm going to repeat that process. I'm going to choose a pivot element here. And we call it a pivot element, just like in basketball, you've got a pivot foot. Once that pivot foot goes down, you can't take it up or it's traveling, right? But you can pivot around it, right? As long as you hold that foot on the floor, you can rotate around it, right? And I'm basically rotating these elements around this pivot element right here. So 9 goes on the other side, 4 goes on that side, 34 goes on the right, 12 goes on the right, 2 goes over here, and 0 goes over here, and then I end up putting 4 right where it needs to be. And remember, we had other sorted stuff over here, sorted. Okay. Now I've got a left partition and a right partition. It turns out that this was the perfect pivot element. Right? We put that element right in the middle. That there were n divided by 2 things over here and n divided by 2 things over here. It evenly distributed them among the left partition and the right partition. And if you do that, it turns out that this algorithm has an extraordinary behavior. Right? Let's go back to our efficiency. Right? Selection sort was n squared. Right? However, this algorithm, which is called quicksort, because it's quick, is going to have an efficiency of n log n. Right? This is sometimes called pseudo-linear. Right? It's almost linear, right? N is linear, but then we've got this logarithmic factor that is multiplied. Right? It's a product of the logarithmic factor, so it's pseudo-linear, or actually pseudo-linear. Sorry, no, a better name, quasi-linear. We use pseudo-linear for something else. Sorry, quasi-linear. It's almost linear. Okay. All right. So how much better is that? We're not going to go through the full coding of this thing, and we're not going to go through the full analysis. I'm just going to tell you that that's what it is in practice, right? Quasi-linear on average, and in the best case, right? In fact, what you can do is you can analyze this thing, and in the worst case, if it's already sorted, you end up pivoting around the minimum element. Then you end up pivoting around the second minimum element. Then you end up pivoting around the third minimum element. And you end up doing nothing, right? And it turns out that that ends up being no better than the selection sort. In fact, it is selection sort. You just get really unlucky and always choose the minimum because it's already sorted. So, knowing that it's n log n, let's go through the same analyses as before. Right? In particular, let's go ahead and, here, it's a good practice for your calc courses if you're taking that right now. What's the derivative of two functions that are multiplied together? You have to use this kind of rule, this product rule, right? Now it's going to be the derivative of n times log n plus n times the derivative of log n, right? Well, the derivative of n goes away and you're left with log n. The derivative of log n is going to be 1 divided by the change of base formula because it's base 2 over n. Well, guess what happens to those n's? Cancel each other out. And it's equal to log n, right? Plus some constant. I don't care. Right? That is much better than linear. It's still worse than a constant with like a linear search. So that's because it's quasi-linear. It's almost linear. Right? Let's look at it from another perspective. Once again, if I go from n, and we'll just jump up here to an order of magnitude of 10n, before it was time t quantified by, n log n, and now it's going to be what? It's going to be 10n times log of 10n. Okay? This is just algebra at this point. What can I do to that log 10n? Log of ab is equal to log of a plus log of b. So I've got a 10n out front, and this ends up being log of 10 plus log of n. Okay? Switch those around, simplify some stuff, and you'll have 10n log n. Actually, you can't simplify too much, but there will be a constant sitting in front here. I don't care what it is. Log of n. There we go. Right? That's just some constant, which is log base 2 of 10, which is 3 point something, times 10, so it's about 40 or whatever, right? Doesn't really matter. Before we had n log n. If I just ignore this lower order term, right, then where are we at? It's only roughly about 10 times slower. Right? That's much more acceptable than 100 times slower. Okay? That's almost linear. That's quasi-linear. Right? So how do we go about implementing this algorithm? We don't. We let the standard library do it for us. Right? So I'm going to throw this together really quick, and it's still running, by the way. Right? How long was it running? It was still running for 9 minutes, so it was more than 7 minutes. Probably because we're investing some time here to create these random arrays. I'll just kick this back down to 1,000 here. Okay. We're not going to use our our selection sort here because it's a terrible algorithm. We've seen even for small data, 400K, it's not going to execute within 9 minutes here or 10 minutes or whatever, right? So what I want to do is I want to not use my selection sort. I want to use the built-in C library function QSort. What do you think the Q stands for? Quicksort, right? It's not necessarily that it has to be an actual quicksort implementation. In fact, 9 times out of 10 it's not, or it's not a pure implementation. It doesn't use, it might use recursion a little bit, but it'll actually use some hybrid algorithms to make it even faster. Right? What I'm going to do is I'm going to sort BRR, or BRR, and I'm going to have to tell it how big it is. I'm also going to have to tell it something else here. What are the things that you are sorting? I'm sorting integers. Right? It needs to know how big that integer is. It needs to know that there are 4 bytes over here and 4 bytes over here because when it goes to swap them, like we did in this selection sort, it needs to know to take these 4 bytes and these 4 bytes and swap only those 4 bytes. Because later on, if I did, say, a double instead, double, right, I'm going to use the same function. Right? There is no QSort for integers, QSort for doubles, QSort for strings. There's only one QSort. Right? It will sort whatever you want, right? But you've got to tell it how big it is. Okay? Because if you tell it that you're sorting doubles and you're actually sorting integers, that means it's going to take these 2 integers over here and swap them with these 2 integers over here because a double is 8 bytes instead of 4 bytes. Okay? It also needs something else. And this something else I'm just going to grab from somewhere here. I'm going to grab it from this morning. Nope, not this one. Where is it? Demo. And I'm going to grab this, and then we'll talk about it here in a second. All right? This is a function. It's called a comparator function that orders integers in ascending order. We'll come back to that. Right? There's a CMP int. Right? I'm going to show you first that it actually works. For that reason, I'm going to kick this down to 10. Just make sure, absolutely sure that it works. And print the array, BRR, of size n. GCC. Oops. Did I already have it in there? CMP int. Looks like I grabbed it from somewhere already. Fine. Yeah. Get rid of that. Yes, it is. It's right there, isn't it? CMP int. Oh, I know it's wrong. I've got this special thing up here that I ended up not using, so I need to get rid of that. Sorry. There. Now we're good. All right. Does it work, first of all? Because if it doesn't work, then we shouldn't use it. But does it work? Yeah. That's sorted. Right. Now let's start doing some tests on it. Let's go back up to 10,000. How much was 10? Or let's start at 1,000 because I remember what that was. That was like point. Oops, I don't want to print that. Let's go ahead and get rid of that now. All right. And let's go back to our timed demo here. There we go. All right. Well, it's kind of comparable to our selection sort. Right? I think our selection sort was maybe 0.003 or something. Right. So let's go up to 10,000. And remember that to 10,000, it was 100 times slower, about 0.1 or something, whatever it was. Right. It's hardly any more than 3 times as slow. Right? Let's go up to 100,000. Remember, 100,000 would have been, what was it? We estimated at 10 minutes? What? 12 minutes or something like that, right? Right. Was there even any measurable difference to the human eye there? Nope. That was way quicker. I can go up to 100, like 10 million here. Is that 10 million? There we go. So I went up 2 orders of magnitude, meaning I went up 100 times as much, right? So this should be 100 times as slow. And it will be, it is counting that random number generator time. But it's about 100, yeah, that's about it, right? It went from 0.01 seconds to a full second. It's 100 times slower. If I were to do the same thing with selection sort, you said it was 12 minutes? And so that's going to be 12 minutes times 100 squared, right? Slower, right? So that's 12 minutes. How many hours is that? Minutes, 2 hours. That's 2,000 hours. It's not even hours. So days? 80, oh, there we go. 83 days. Let's just bump it up to 3 months there, right? 3 months versus 1 second. Is there any comparison? No. Right? So, how does this thing actually work? Well, it's kind of the implementation that I just talked about. We should understand this and this pretty well. We should also understand this because, of course, if it's swapping things around, it needs to know how big those things are, how many bytes it's swapping. But what the heck is this thing now? Let's go ahead and take a look at it. Okay? Yeah. Okay. This is what's called a comparator function. All right? Qsort, quicksort, is a generic sorting function. It's a generic sorting algorithm, right? It can sort integers, it can sort doubles, it can sort strings, it can sort whatever you want. But it doesn't know how to order them. Right? Instead, what it has are these generic void pointers. It's a pointer to something in memory. It's a pointer to something in memory. What are those things? Right? Qsort has no idea what they are. So if I've got A and B, how do I tell that A comes before B or B comes before A or that they're equal? Right? And now I don't need to swap them or something. I need a function to tell Qsort how to do it. And the function works as follows. It takes 2 generic void pointers, const because we are making a promise that we're not going to make any changes to your integers. Okay? Void star, that's not an integer though, right? That's okay, because we're going to make them integers here in a second. And then we return a value here, an integer. The way that it works is we force A and B to become const int stars. Now they are integers, right? Now we can take a look, and that one has a value of 42, and that one has a value of 72. So 42 comes before 72, right? And once we've got x and y, we've forced them to become integers. We can then start making comparisons. Right? Why do I have a star right here? What is that doing to x? What type of variable is x? Is it just a regular old integer? No, it's an integer pointer. I want to look at the value stored in x, so I dereference it. I want to look at the value stored in y, so I dereference it. Once I've dereferenced them, now I've got that 42 and 72 value. If 42 is less than 72, I return something negative. Right? If it's just the opposite and 72 is greater than 42, then I return something positive. Otherwise, what's the only other case? They're equal. And if they're equal, I return 0. I've seen this before. Where have we seen this before? String comp. strcmp. Man page. Man is short for manual page. And let's see if we can read all about it here. All right, there we go. It's a function that compares two strings, S1 and S2. Here's the contract. It returns 0 if they are equal, if the contents are equal, apple and apple. It returns a negative value if S1 is less than S2. In other words, apple comes before banana. Right? It returns a positive value if S1 is greater than S2. Banana comes after apple. Right? This is a contract. This is a pattern that is in every single programming language that you'll ever encounter. It's called a comparator pattern. Does it go like this, or are they equal? Negative, positive, 0. Right? Those are the values that a comparator returns. Okay? And that's what this is doing over here. It's telling QSort, given these two generic values, you don't know how to order them, but I do. So I'm going to go ahead and force them to become integers, dereference them so I can look at the values, and then I will tell you, oh, they're in order, or that you don't need to swap them, or they're out of order, you do need to swap them, or they're equal, right? Don't swap them because the 4, 4, 4, 4, 4, all the 4s would be together there. Right? QSort needs to know that, right? So we have a picture that looks something like this, if I can pull it up. Come on, everything is slow today. I'm fine on power. I don't know why it's not coming up. Let's see. Comparator diagram. Here we go. Come on. Opening up from the cloud takes a long time, apparently. Right. Okay. We've got an array. There we go. Now that's better resolution there. We've got an array that is given to this sorting algorithm, QSort in this case. Right? QSort doesn't know how to order those things because they're generic. Right? You could give it an array of integers. You could give it an array of doubles. You could give it an array of students or airports, like you're going to be doing after the break. It has no idea what the hell that stuff is. So it has no idea how to order them. It knows how to sort them. It knows that if this one goes before this one, then I arrange them like that. Right? But to answer that question, it takes that A and B, and it hands it off to this comparator function over here. That comparator function returns something negative, 0, or positive, depending on the relative ordering of those things. Okay? Now, we'll look at, after the break, we'll look in much more detail on how to write these things. But now that we've got one for integers, we can start doing a whole bunch of other stuff. Right? Let me go ahead and kick this down to just 10,000 here. Right? No more am I going to write my own sorting algorithms. Selection sort, that's out the window. Right? Because I already have something built in for it. Right? But also, I'm no longer going to write my own linear search or B search algorithms. Let's see, B search, C man page. There we go. Where is it? There we go. What do you think the B stands for? Binary. There you go. Binary search. And it's in the standard library. And it has essentially the same, what do I want to say? The same pattern here, right? But there's this new value here called key that you're actually searching for. Right? So int key. Let's search this for 42. Okay. So B search. I'm going to have to pass in a pointer to it. So how do I take the key and make it into a pointer because it's a regular old variable? Ampersand. Otherwise, it's exactly the same thing as over here. You want to search the array called BRR, which has n elements, and it contains elements of 4 bytes, or whatever it happens to be. And I'm going to use this comparator to ask questions of, I'm going to compare it to the middle element. If it returns 0, I know that I've found the element that I'm looking for. If it returns positive, then that means that I know that I should be searching the left half, or the right half, or whichever the case may be. Right? All right. What does B search return? A generic pointer. Right? It does not return an integer pointer because it doesn't know that you are sorting an array of integers. It doesn't know that you're sorting an array of doubles. It just knows that you're sorting an array. Right? So like malloc, we have to force it to become a pointer. PTR is equal to, you can do it this way, or you can leave off the typecast if you want to. Right? All right, so is it in there? Printf found %d at memory location %p and the line. Right? And then we will say key and PTR. There. GCC. And we can time it, whatever. Found 42 at that memory location. Right? Cool. I don't have to write my own binary search either. Right? I don't have to write my own linear search either. There's lfind, right? And we can look at that after the break as well. But let's see. What else did I want to say on this? Oh yeah. Let's get rid of this. Right. Remember when we tried to use binary search, but we didn't know how to sort yet, and it failed? All right, it's not going to fail there. Let's kick this down to, I don't know, 10. There we go. And let's ensure that it's actually in there. What I'm going to do is I'm going to say, after you generate that random array, make the last one equal to 42. Right? So this should end up as a successful search, right? Because I've, oh, by the way, if it's an unsuccessful search, what does it return? Yeah, nil. It printed it out as nil here, but it ends up returning null, right? So let me run this one more time, right? All right, but wait a second. I cheated. I made sure that the last one was 42, but it's saying that it couldn't find it. Why? Same problem as before. It's not sorted, right? So it has to be sorted in order for binary search to work. There, 42 at memory location. Oh, come on. It should be in there, right? Key. Maybe I just went too fast. I didn't actually save it. There. No, that's not it. Okay. Oh, there. No, come on. It's working. What's wrong? It's definitely going to be in there. We're always searching for 42. Why are you not finding it sometimes? I mean, I cheated. Do you see anything? Thank you. Perfect. Because I changed it after I sorted it. I should change it and then make sure that it's still in there, right? So there we go. It's always going to find it now. And of course, the memory locations are going to be different because every time I run the program, it loads it up in a different memory location. Okay. There. It's got to be sorted. There is also a linear search, lfind, see man page. There we go. No, not find. I want lfind. There we go. There it is. All right. Find an entry using linear search. So, for example, if I came over here and I said I did not want to search it, then I can change this to not binary search, but I can go ahead and use a lfind. Lfind. And let me make sure that that's the correct. There's the key. There's the array. There's the number of elements. There's the width, which is what they call the number of bytes, and there's the comparator that you use for it. GCC. Oops. Sorry, where is it? It's in the search library. It's not in the standard library. So let's go ahead and bring in the search library now. It's probably not standard because why would you want a slow search, right? Oops. Yeah, you can ignore that. Never mind. GCC and let's run it. Oh, come on. You can't ignore that? What's the... okay, so base, number of elements should be size T. All right. Pretty sure that this is okay. Okay, I'm not sure why it's segfaulting. 42. It does return a pointer to where it should find it. I'll have to dig deeper into that, but you don't have to write your own linear search algorithm, right? And there's also, I think that there's also a version of L-Search that will search, and if it's not in there, it'll insert it for you at the end of some sort. But otherwise, there you go. You don't have to write your own code to do this. When you come back next week, you will write your own code so that you can go through the pains of seeing what it's like. But afterwards, when we cover this stuff in detail, you don't have to do that anymore. Just use qsort, bsearch, or lfind. All right, we're good on time. So, any questions? No. So when we come back on Monday, we'll explore what this is in further. Basically, this is what's called a function pointer. So int star a, what is that a pointer to? That's an integer, right? Well, what is this thing right here? That's a function. Integers and functions are stored in memory. So what you can do is you can create a function pointer as well. You can create a pointer that points to an integer, right, just like this. Oops. Undo, copy, right? Just like that. You can create a pointer that points to a function. Right? And CMP int, the name of the function, ends up being its pointer. You're just referring to a piece of code stored in memory. Qsort, use that piece of code over there in that in memory so that you can decide if A and B need to be swapped or not. Right? There's the comparator over there that I want you to use. Versus there's a comparator over there that I want you to use. Right? All you're doing is passing in a pointer to this the memory address storing that function. Right? CMP ends up being the pointer itself. All right, we'll give a primer on Monday of how to exactly do that. Okay. Otherwise, have a good break, and remember, there's nothing next week at all.